A complex number is defined as a number of the form a plus iota b, where a and b are real numbers and iota is the imaginary unit defined as the square root of -1. For example, 2 plus 3 iota and -1 plus 4 iota are complex numbers. In such numbers, the real part is a and the imaginary part is b. The concept of complex numbers allows us to find solutions to equations that have no real solutions. For instance, the equation x to the power 2 plus 1 equals 0 has no solution in real numbers, but it has complex solutions. If z equals a plus iota b is a complex number, then a is called the real part, denoted by re of z, and b is the imaginary part, denoted by im of z. For example, if z equals to plus 5 iota, then re of z equals 2 and im of z equals 5. Complex numbers are used widely in electrical engineering, fluid dynamics, and quantum physics. Understanding complex numbers is also key to solving quadratic equations where the discriminant b squared minus 4ac is less than 0. Two complex numbers are considered equal only if both their real parts are the same and their imaginary parts are the same. In other words, if z1 equals a plus iota b and z2 equals c plus iota d, then z1 equals z2 if and only if a equals c and b equals d. For example, 3 plus 4 iota is equal to 3 plus 4 iota. But 3 plus 4 iota is not equal to 4 plus 3 iota because here the real and imaginary parts are swapped. This property of equality is very important when solving complex equations and verifying solutions. Equality is always checked component by component. The real parts must match exactly, and the imaginary parts must also match exactly. The addition of complex numbers is done by adding their real parts together and their imaginary parts together. If z1 equals a plus iota b and z2 equals c plus iota d, then their sum is z1 plus z2 equals open bracket a plus c close bracket plus iota times open bracket b plus d close bracket. For example, open bracket 2 plus 3 iota close bracket plus open bracket 5 plus 2 iota close bracket equals open bracket 2 plus 5 close bracket plus iota times open bracket 3 plus 2 close bracket. That simplifies to 7 plus 5 iota. This operation is commutative, meaning the order does not matter, and it is associative, meaning grouping does not change the result. Also, addition of complex numbers is closed. The sum of two complex numbers is always another complex number. Multiplication of complex numbers works like algebraic expansion. If z1 equals a plus iota b and z2 equals c plus iota d, then their product is z1 times z2 equals open bracket a c minus b d close bracket plus iota times open bracket a d plus b c close bracket. For example, multiply open bracket 3 plus 4 iota close bracket by open bracket 2 plus 3 iota close bracket. Expanding, we get open bracket 3 times 2 minus 4 times 3 close bracket plus iota times open bracket 3 times 3 plus 4 times 2 close bracket. That simplifies to -6 plus 17 iota. This multiplication follows the distributive property, and the result is always another complex number. Geometrically, multiplication has a very interesting meaning. It combines or multiplies the magnitudes of the two numbers and it adds their arguments or angles. This means multiplication in the complex plane produces both a scaling and a rotation effect. The conjugate of a complex number z equals a plus iota b is written as z bar equals a minus iota b. The modulus of a complex number, written as modulus z, is defined as the square root of open bracket a squared plus b squared close bracket. For example, if z equals 3 plus 4 iota, then modulus of z equals the square root of open bracket 3 squared plus 4 squared close bracket, which equals the square root of 25 or 5. The modulus represents the distance of the point from the origin in the Argand plane. Let's quickly recap. Complex numbers are written in the form a plus iota b, where a is the real part and b is the imaginary part. We learned how to check equality, how to add and multiply them, and how to find the conjugate and modulus. Complex numbers are powerful because they allow us to solve equations that have no real solutions. They are also widely used in mathematics, physics, and engineering. By understanding complex numbers, we gain a tool that extends beyond real numbers, opening doors to deeper problem solving and real-world applications.